back to the channel, Derivability. This is where we show derivations and proofs of a lot of things you see in introductory or maybe sophomore level physics and engineering, maybe some math, calculus, trigonometry. Okay, and it was recently suggested to me that maybe I should do a series of videos on hyperbolic functions, and I thought it was a great idea. And I've got several videos planned. I'm going to put them in a playlist, of course. And no better place to start than the beginning here. So let's do that. So what are hyperbolic functions? Why do we have them? What's the motivation? Okay, so probably you are familiar with what we call the parametrization of the unit circle. Okay, that is the circle whose equation is x squared plus y squared equals 1. Okay, and we can parameterize that, so-called, using sine and cosine functions. The geometry of that, in terms of like opposite sides, adjacent sides, hypotenuse, literally just using some triangles, is pretty straightforward. Okay, so if we say that, in other words, we parameterize x as cosine theta in terms of this variable theta, and y in terms of sine theta. This is handy because our unit circle has this equation, x squared plus y squared equals 1, and if we let x equals cosine theta, y equals sine theta, well, they obey this same equation. It's called a trigonometric identity. Cosine squared theta plus sine squared theta equals 1. All right. Now, when you take analytic geometry, calculus, in high school or college, wherever that might be, you also learn about conic sections in general. Okay, that is shapes that are sections of a cone when you slice a cone with a plane. All right, and we actually come up with something called a hyperbola, and in particular a so-called unit hyperbola. Okay, so if we have instead x squared minus y squared equals 1, okay, we get the shape you see on the right, okay, with some dashed asymptotes. Those are lines that the curve approaches as it travels further in the diagonal directions, as you see there. Okay, so a reasonable question could be, is there some way that we could parameterize the unit hyperbola, like x in terms of some variable, y in terms of the same variable, different functions, so that we get, you might say, an identity, such as we do for the so-called circular functions, the normal trig functions. Okay, turns out that we can do that. Okay, then the way I'm going to approach it is I'm just going to say, I'm just going to make up these functions, and in analogy with the circular trigonometric sines and cosines, I'm going to call these hyperbolic sines and cosines. Of course, I didn't make that up, but that's what they're end up going to be. And the notation is we just put an h on the end of everything. So for the hyperbolic cosine, COSH, and I'm going to use some variable u. We pronounce this often cosh, so cosh squared u, okay, minus, and then hyperbolic sine, okay, that is SINH. Sometimes this is pronounced sinh. So sinh squared u, okay, cosh squared u minus sinh squared u, we want to equal 1, okay, and again, that's if x we parameterize as cosh u, and y we parameterize as sinh u, okay, so-called. All right, well, we haven't really done anything here. We've just created these names and functions. We don't know anything about these functions yet. Okay, but they have a lot in common with trig functions, not just the names and the notation, but a lot of formulas are very, very similar. Identities, for instance, trigonometric identities, what we're going to see eventually in our series of videos, some today, are hyperbolic function identities. All right, and then there's lots of applications, lots of things that are very, very similar. All right. Eventually, what I would like to do is in my one of my latter videos, of course, I haven't done yet, but I'm going to be getting to is a physics and engineering example where we figure out the shape of a cable hanging under its own weight. All right. And this is something that that you do in like a physics or mechanical engineering class. And a lot of other my videos are on those topics. So we're kind of working up to that. Okay, so let's talk about exponential functions and how they are related to both the circular functions and the hyperbolic functions. All right, well, next let's take a look at the exponential relationships with the sine cosine using something we call Euler's formula. Okay, now don't panic if you've never seen this before, because we're not going to focus on this, but we are going to make an analogy with the hyperbolic functions. Okay, the I here is what we call the imaginary unit. I squared equals -1. Okay, so E as the base of the natural logs, e to the I theta equals cosine theta plus I sine theta. Okay, what we could do is we could take the complex conjugate of this expression and write e to the minus I theta equals cosine theta minus I sine theta. Okay, and what can be done with this now is we can think of the sine and cosine theta as variables and think about this as two equations and two unknowns. Okay, so we can solve this for cosine theta and sine theta in terms of e to the I theta and e to the negative I theta. Okay, so again, maybe you've seen this before. If you haven't, don't sweat it. Okay, because chances are you'll see it very soon, or there are a lot of good videos out there on Euler's formula. There's really no need for me to reinvent the wheel on that. I'm sure you can find one somewhere. All right, so those are our formulas for sine and cosine. Okay, now it turns out that we can generate an exponential formula for these hyperbolic sines and hyperbolic cosines. Okay, so what I'm going to do now is I am going to start with hyperbolic cosine cosh of u. And what I'm going to do here is I am just going to, basically get rid of the imaginary stuff. Okay. Now this is not really too motivated, but I think what we're going to do, what we're going to finally find out here, is that that this works. Okay, so cosh u, I'm going to say, is 1/2 e to the u plus e to the minus u, and sinh u, okay, 1/2 e to the u minus e to the minus u. Okay. All right, now what you can do here is kind of go in reverse, kind of compared to what we did in the blue up there. You can treat e to the u and e to the minus u as, you might say, the variables, and think of these as two equations and two unknowns. All right, and so what you can find here is that e to the u is the same thing as, I'll do the cosh first here, excuse me, cosh u plus sinh u, and then e to the minus u, okay, cosh u minus sinh u. Okay. All right, so, kind of one way of looking at it, another way of looking at it in terms of solve for the hyperbolic functions or solve for the exponential. Okay. All right, now what I want to show you now is that this invention of these new functions, cosh and sinh, in terms of the exponentials, actually successfully parameterizes our unit hyperbola. Okay. In other words, what I want is to explore cosh squared u minus sinh squared u in terms of the exponential functions just above here, and see that doesn't matter what the variable u is equal to, that we're always going to get the number 1. Okay, so let's do that. All right, so what I'll do is I will FOIL out cosh u. Okay, so there's a 1/2 in front, so squared, that's 1/4. Okay, then doing the normal foiling operation, so to speak. Okay, I square the first term, e to the 2u. I take double the product of my two terms. Well, that just ends up being 2 because e to the u and e to the minus u are reciprocals. And then I square the last term, okay, e to the minus 2u. Okay, now I'm going to do the same thing with the sinh expression here. I'm going to square that out. I get 1/4. Okay, the only difference is in the middle I get a minus 2. Okay, it's like that. All right, so again, if you need to pause the video just to kind of verify that I've done my foiling correctly, I think you would be well advised to do that. Okay, not necessarily to check me, of course, but just to check yourself. Okay, now notice here I'm subtracting, so if there are any identical terms, they will cancel. Okay, so the e to the 2u's cancel. There's a 1/4, of course, it's common. This one will be positive, this one will be negative. Okay, likewise with the e to the minus 2u terms. Okay, so what I end up getting here is a 1/4 times 2, that's a half. And then a minus 1/4 times a negative 2, that's another positive 1/2. And I get 1. Okay, so in other words, that really does provide an adequate parameterization of the unit hyperbola. Okay, so if you're willing to go along with these definitions in terms of the exponential functions that I've got starred over here, then, well, we've succeeded in parameterizing the unit hyperbola the same way that maybe you've seen the parameterization of the unit circle, which is a little bit more common. Okay. All right, now what I want to do is show you just a couple more things here, because I don't want the video to go too long, of course. All right, so what we are going to do next is just take a look at a couple of identities. We'll prove a couple of identities for hyperbolic functions that really ought to remind you of some trigonometric identities. Okay, well, here we are back. All right, so what I did was I wrote down kind of the so-called basic Pythagorean identity that we have for the circular functions, which you know, I'm assuming you know here, cosine squared plus sine squared equals 1. Okay, and then the corresponding hyperbolic identity, which we've already discussed, is cosh squared minus sinh squared equals 1. Okay, they're very similar, except, you know, sometimes you have a minus sign in there. Okay, so let's do a couple of other straightforward identities from trigonometry that you have probably learned and proved using other methods. Okay, and then let's just kind of see what we get when we try to do something similar in the hyperbolic realm. Okay, so for the hyperbolic identity, what I want to do is start with, say, see if I can get a double angle identity for sine 2 theta. Okay, what I'm going to do is I'm going to, or sinh of 2u. What I'm going to do is I'm going to start with 2 sinh u times cosh u. And I'm going to use the exponential definitions and see what happens. So I have a 2. Okay, now if you go back in the video, I can kind of reset, rewind, and figure out what to plug in for these. The sinh u was e to the u minus e to the minus u. Okay, and then 1/2 in front. Cosh u, 1/2 e to the u plus e to the minus u. All right, so you know, we got a few things canceling here like that. Okay, then I'm going to have a 1/2 that's left over. Okay, then I need to multiply these two binomials. And kind of the good news there is that this is kind of like an a minus b and an a plus b. And of course, you guys know when I multiply those, you get a squared minus b squared. Well, in our case, that's going to be e to the 2u minus e to the minus 2u. Now, this is like totally identical with our exponential definition of the hyperbolic sine function, except instead of u, it's 2u. So this is really the hyperbolic sine of 2u. Okay, so what we have here is a very nice double argument identity. Okay, sometimes it's even called a double angle identity, even though u doesn't literally represent an angle. Okay, but anyway, a double angle, double argument identity. In this case, it is exactly the same as its cousin over there with the circular functions. Okay, there is no funky minus sign that comes into things. All right, so in this case, it's exactly the same. Okay, all right, now a person might wonder then, is if we go on to the next identity, okay, maybe the one for cosine 2 theta in trigonometry. Okay, because I have a minus sign here, maybe I'll have a plus sign in the hyperbolic side. Okay, you know, our guess there is maybe, you know, kind of trading the plus for the minus in our Pythagorean identity up top. Okay, so maybe we're going to trade the minus for the plus. Yeah, we'll see. You know, it's a guess. Okay, so now let's start with the right-hand side of the cosine 2 theta identity. And in this case, let's take cosh squared u plus sinh squared u. In other words, I'm kind of trading the minus for the plus. Okay, and then we'll use, once again, we'll use the exponential definitions here and see what we get. Okay, well, cosh, remember, is 1/2, and then the grouping e to the u plus e to the minus u. Okay, that whole guy gets squared. And then for sinh, 1/2 e to the u minus e to the minus u. Okay, that whole thing gets squared. All right, so let's expand those out. Okay, we did this before up on one of the previous screens, except in the middle we had a subtraction. Okay, so I'll go through it quickly since we've already done it. Okay, again, the difference is we're kind of adding in between the groupings. There's 1/4 there. Okay, now in terms of getting things to kind of combine, reinforce, versus getting things to cancel, okay, because there's a plus sign in between here, I noticed that I'm going to have a 2/4 and a minus 2/4 after I distribute that 1/4. Okay, otherwise, I have identical terms going on here. So I have a 1/4 plus a 1/4 of those. That gives me 1/2 e to the 2u plus e to the minus 2u. And very similar to my explanation up here, okay, this looks exactly like our cosh definition, except I have 2u instead of u. So yes, indeed, just like we may have guessed, the cosh 2u identity kind of reminds us of the cosine 2 theta identity from trigonometry, except there's that, you know, we trade off a plus sign for a minus sign. Okay. All right, so I think what I'm going to do here is conclude here in a few minutes. And before we go, I think what I might do is just paste up, without proving, I'll just paste up some other identities in the circular case and the hyperbolic case. And you can see how some of them are similar, how some of them are different. You know, maybe take this as a challenge to prove some of those new ones on your own. Okay, I think it's kind of fun to see how some of them are the same and some of them are different. Okay, so I'll paste a few up here in a minute, but otherwise, I'll say goodbye, and thank you for dropping in. And hope you can give me a like and subscribe. Share this with your friends and classmates. And we'll hopefully see you for the next in my series of hyperbolic function videos.